Thank you very much for the very nice introduction. Yes, the name is pronounced correctly. It's Brian Pauw. It's a Dutch name. So yeah, I am originally from the Netherlands, but I traveled around the world a bit. I spent some time in Denmark for my PhD, postdocs in Japan, and about 7-8 years ago we moved back to Germany. I will tell you today about X-ray scattering and about lab automation. It turns out that these two things have a surprising amount of aspects in common, including things like digitalization, automation and simulation, which are reflected exactly in the lab automation aspects. So the reason why we started looking at things like data organization, metadata collection, was to try and combat some of the problems that we have in science. Now, there's a lot of issues that are currently playing a role in science. Dr. Lutz Bohm has a beautiful list of all the crises that we're suffering. One of these crises is a reproducibility crisis, and this is the problem between what we think science should be and what it actually is. Now, one of the core tenets of science is that it's independent of the researcher and that anybody can reproduce an experiment. In reality, however, this turns out to be very, very difficult. And it's funny to me because over the last 15 years, I've seen these reproducibility crises get closer and closer. I mean, they started in the field of psychology, and we looked at it and we were like, yeah, but it's psychology. Then they moved closer to medicine, biomedicine, biology, chemistry, and now they've arrived in physics. So this is about a 15-year span between these things. And the reason I think that we're suffering from these reproducibility crises is the traditional way that we're doing science. In the traditional way, we are looking at or we're doing parts of our experiments as if they're completely isolated from everything else. So we're doing syntheses, we're doing measurements, we're doing corrections to the data and analyses, and then the traditional scientist sits down, looks at his lab notes, strokes their beard if they have one, and hopefully waits for a spark. You know, hopefully a spark arrives and he comes to a scientific finding. And a process like this is inherently irreproducible. You will not find two scientists who think alike. You won't even find two scientists who are able to read each other's notes. So turns out we can actually measure this. Here's a bit of research. This paper was accepted last week. It's a very simple round-robin study that we did to try and assess what the influence of the researcher is on scientific findings. What we did is we sent around 4 data sets. And I sent them around to my colleagues and I said, look, please analyze these data sets as you normally would. And here's some pieces of information which you normally would have, things like sample composition, general shape of the scatterers and so on. And give me these sort of key metrics of the size and size distribution that you want. And the results that came back were much less comparable than I would like them to be. Now, I have some standards, of course, but even so, some things were very hard to compare indeed, like the width of the distributions. And this is not a problem of the data, it is solely the effect of having a different researcher look at the data. So we know this is a problem, so we should improve. I mean, what's the point of doing science if you always do science in the exact same way as you've always done? So, you know, in the words of Maya Angelou, I did then what I knew how to do. Now that I know better, I do better. Certainly words to live by, and certainly things that we try to approach. And nowadays, it's become very easy to do things better, and that is because of the advent of computers. Now, computers have been around for a while, but they allow us to record every single step that we do to our data and to repeat if necessary. In addition to that, if you integrate this with lab equipment, you can have computers record every process that happens on your laboratory equipment. And this can be even more powerful, so you don't rely on the researchers writing things down. Turns out humans are very unreliable in this, so you better have computers write down everything that you do. I promised I would talk a little bit about small angle scattering. Small angle scattering, in brief, is a technique that allows you to measure X-ray scattering patterns, as shown on the left-hand side, and to interpret this information to get things like sizes and size distributions and volume fractions for the fine structure in your samples. These sizes generally range from sub-nanometer range to a few hundred nanometers. You can extend this range if needed. But the problem with X-ray scattering, and the reason that I sort of rolled into this whole metadata story, is that you can see that the X-ray scattering information is very low in information density. So that means that if you make a mistake in the way that you process your data or in the way that you analyze your data, there's nothing, there are no guardrails or something. There's nothing to indicate that you've gone off the rails, that there's something wrong with your data. You can still do the analysis, you can still get numbers out, and as we all know from academic literature, it's still possible to hand wave away any differences between this technique and other techniques. It does not have to be, though. I'm getting a little bit ahead of myself. I just wanted to show you a sort of cross-section of the materials that we analyzed over the last 5 years. We've taken a look at inorganic materials, and these include things like metal alloys, but also mesoporous silicas, at polymers and composites, very interesting for the material science community. We've looked at biological systems, including teeth, bone, hair, and human blood. I will try to stay away from human blood in the future because it's super sticky to work with and it's very cumbersome. It gets everywhere. I would not advise working on that, but it was interesting nonetheless. We're also working a lot with geological materials. This is of great interest to to sort of the large-scale industry related to construction and building construction and so on. They're very interested in the way that particles form and that their structure in their materials form. But we can also study complex systems. One of the things which I really liked is that a few months ago we managed to put a whole pouch cell in our X-ray beam. Get an X-ray beam through, and we could see how the fine structure of this battery was changing as we were charging and discharging this battery. So that, you know, it's a very complex system, lots of different things in there, but somehow you can still get some information out of these. The technique itself is super simple to do, hard to do right, but when you just want to do X-ray scattering, you take an X-ray source, monochromated X-ray source ideally. You cut this beam down with the help of a collimator to about 0.5 millimeter in diameter, so that you end up with a very parallel small beam. Electron density differences inside the sample will cause a small fraction of the radiation to be scattered and diffracted. We now stop the unscattered beam by means of a beam stop, mostly to improve the signal to background ratio. And we collect the scattered and or diffracted radiation on our detector. It usually looks something like this. This might be familiar to some of you. This is, of course, diffraction. Now, diffraction is what you see if you have put your detector very close. But we can move the detector further and further back, with a concomitant improvement in collimation, we can then zoom in to the central section of the previously just diffraction pattern. and measure smaller and smaller scattering angles. And by looking at smaller angles, you're actually investigating larger and larger structures. I developed a bit of a statistical method to combine these data sets into a single curve. So that would look like this. Interestingly, on the vertical axis, note that we're covering almost 9 orders of magnitude in intensity. So there's a huge dynamic range there. On the horizontal axis, this is the angle axis, we're covering almost 4 decades in angle. And that means that we are probing almost 4 orders of magnitude in size information from our materials. So we have in here information on the crystalline distances and a crystalline structure that might exist in our material. We have information on the particle size and particle size distribution. And in this case, these particles were actually dispersed in a porous carbon catalyst material. So we also have information on the porous carbon carrier itself. Note that for X-ray scattering to happen, you don't really need crystalline material. You just need an electron density contrast. So if you have voids in a polymer, you can measure the size distribution of voids just as well as you can measure these metal oxide particles in a carbon matrix. Now, to me personally, it's very interesting that the intensity that we measure is directly correlated to the electron density in the material by means of a Fourier transform. Now, Fourier transforms are cool. For those of you who are not familiar with it, I highly recommend it. They're super useful tools. Unfortunately, however, we're not measuring the entire Fourier transform. We're only measuring the amplitude square. So the intensity component of the Fourier transform. And that means we've lost information. We can no longer inverse Fourier transform the intensity to get our electron density distribution out. So we have to be a little bit more clever about how we go about analyzing this. And this is the phase problem in diffraction, and it's Babinet's principle in small angle scattering, but it's exactly the same problem of loss of information. One thing you can do is to Fourier transform any sort of conceptual model that you have of the structure inside your material, and then you can compare your measured versus your model intensity. That comparison, of course, works best if you bring your model and your data as close as possible together, which means that you need to account for reality in your model and correct for imperfections in your data. And this is where you start getting the need for really good metadata. And this is why you need to record as much information as possible on your material and on the way that you've done your measurements. All that to reduce alternative interpretations. Now, in real life, the instrument looked like this. Well, the instrument that we have currently installed looked like this. This came about 6 years ago. We pretty much immediately took it apart because this machine was built, as you can see, with the idea that there's a human there. And our laboratory is very much understaffed, so it's pretty much, at the moment, it's only me. For the last 5 years, I had a good colleague, Dr. Glenn Smales, who helped me out developing this machine. But even with 2 people, you cannot afford to have a human constantly in here. So we changed the machine. We replaced a lot of the hardware and we replaced a lot of the software as well. And now this machine can run through racks of samples over the time span of 2 to 3 weeks. So right now it's also measuring. It's actually measuring a great amount of time, as I will show later. I wanted to go a little bit in depth in how we actually organize what the methodology is of our measurements in here. Just as an example, I don't think anybody should follow this, but it's just to show you how complex this thing gets once you start automating these. And we normally start with discussions with the users. They give us Excel sheets where they've filled in a couple of details about their project and about their samples. We take this information and we fill out an electronic logbook. Sounds super fancy, is just an Excel sheet. which we now use as the single source of truth for all of the data correction. So all of the data that is entered is only entered once. Once you have to enter things twice, people get bored and they don't do it. So everything is only entered once. I have a Python script that reads this Excel sheet, generates a measurement script from it that's fed to the machine, and the machine starts doing its measurements. After it's done, we collect the files. Machine spits out a number of different files which need to be collected and organized. That is then converted into a Nexus format that we can use, and into that is fed information from the electronic logbook and from some sample information from the proposal form. And we do this because we need metadata that is not available to the machine, like who is the user, what's the sample name, what atomic composition do the different phases in the sample have. Then we do a very quick thickness calculation from the X-ray absorption that we measured. We do a data correction procedure. I'll show this a little bit later. As you remember, we measure at different distances, so these get automatically merged. These nowadays also get automatically analyzed, at least with a cursory data analysis, and then it can move on to interpretation. So this is a huge chain which is involved with these experiments. We try to log as much as we can into a data catalog. We use SciCat for this. It's a data catalog which is being developed at the European Spallation Source. And it's very handy for me because it's a low barrier of entry for me to dump data into. But you could use anything really, as long as your data is in a format that allows you to read all of the necessary metadata. It doesn't really matter what you upload it to. Now, this is a very schematic way of looking at things, and I kind of started wondering, what does it look like in reality? Well, I started drawing that out, and it sort of got out of hand. This is how we really do our experiment, and you see, there are some things in this process that are logged into the SciCat database, like information about the sample, information about the project and the users and so on, raw data, process data, merged data. But there's a lot of information which is still not captured by this data catalog, which might also be of interest. Now, a lot of this information ends up in the metadata of the files, but some of it doesn't. Especially when you then get to the analysis portion of the experiment, things really don't work out anymore. You know, we want to catalog our analyses in our data catalog as well. But things like interpretation, which needs information on the domain knowledge of the person who interpreted it, that is really hard to capture in this. However, it is my goal that one day we will be able to do this and hopefully work towards a more traceable and trustworthy science. Just as a side note, one of my colleagues, Petr Shermak, actually mentioned that we should put a T behind FAIR data, not just because it sounds funny, but also because with the T you can indicate the trustworthiness of data, which means that, you know, a certain measure of how much you can actually rely on this data. All right, take a couple of steps back. I mentioned that we have actually improved the efficiency of the machine. Now, the improvements that we did, this entire experimental chain, have led to us improving the usage efficiency of our machine. Now, in 2018, we already had the electronic logbook and the conversion. We were actually able to use, to expose our detector during that year for 32% of the hours in the year, which is great. But the subsequent years, the improvements that we did made us more than double this. So instead of buying a new machine, you could actually get efficiency improvements just by looking at the way you do things and trying to make things better. Now, much of that ended up in papers. This is great. Management is very happy with output like this. For us, though, it's not really that important that the numbers are great, but more that the data that ends up in these papers is trustworthy. So We also try to upload our datasets for papers to Zenodo separately. I do sometimes not find the time to do this, but it is certainly the aim, and many datasets are already there. And with these efficiency improvements, we're really churning through samples. Now, last year we did 700 samples per year. This year we're going to do about the same, which means in total we've measured more than 2,000 samples for over 200 projects for over 120 collaborators. And you can see that this starts needing more and more organization, because now you need to be able to find the measurements you did for a certain point, for a certain person on the specific sample in a particular point of time. Nevertheless, I'm happy with this. All right. So we started, as you could probably already tell, we started looking at the whole experimental procedure as a more of a holistic process, right? Not as individual separate components, but as the interlinked combination of the aspects that make up an experiment, like the sample preparation, the measurement, the collection, the correction, the analysis, and the interpretation. I've shown you a bit about the measurement and how that is done. We also developed a universal data correction procedure. This is great because it works for all samples that we throw at it, both in our laboratory and at the Diamond Light Source, with whom we developed these. That's sort of 5 years of my life there. I also worked on data analyses that you could do to all of your data, well, most of your data. That gives you form-free size distributions, so you don't need to tune your analysis so much to a particular sample. And I worked on interpretation. I will show you this particular interface in a moment. Now, this is nice and sequential and so on, but on top of that, you also need organizational systems. And one of the things that really helped us was Rundeck. This actually turned out to be much more useful than we thought it would be. It is a very simple thing. It's a web interface that allows you to sequence your data processing steps. So here we have, I don't know, 8, 9 data processing steps that have all been chained together as part of our data processing pipeline. And I can use this, my colleagues can use this, and when something goes wrong, I can go back into the logs and find out what went wrong for their particular case. So this, yeah, easy to set up. Nice pragmatic solution. SciCAD, I've mentioned it before, it looks like this, allows us to dump all of our measurements and catalog all of our measurements in here. We can actually search on things, on metadata like this, and filter our measurements and try to dig into the metadata to find out things that are wrong. What we're also doing is automatically flagging our measurements for common issues. Things like if the transmission value was too low, what could this be related to? We're just flagging this. Or if your flux values are fluctuating, which means your machine is not stable, what would that be related to? Now, in order to do all this, we also needed to think about how to structure our data. I will actually show you this in real life because it's more interesting that way. So I have an interface here. It's called Dawn. It's the data analysis workbench developed at the Diamond Light Source. And I have one of my measurements over here. And I will show you, if I can get my fingers to work correctly. There we go. I'll actually show you what's inside there. So we have 2 groups. One is the raw measurement in the Nexus format, and one is the process data. So in the raw measurements, we can actually see information on the sample. That has things like name and what sample holder it was measured in, but also information on the beam flux and the wavelength at the sample position. We store things like the additional thickness that we derive in one of the data processing steps. We store that in here. Of course, everything with the units and, if possible, with uncertainties. And yeah, there's a proposal number. I should put more information in here. I actually have a newer format of this data format, which also has things like LaTeX or BibTeX citations that people can use and so on. It's overkill. But in the instrument section, we actually, you can discover how the experiment was done without actually knowing anything about the experiment. You see that we have a source, we have a monochromator, there's a detector in there, there's a beam stop in there. For each of these you have locations where they exist in three-dimensional space. And when you get to the detector section, things get really ridiculous. And that's because the detector we're using, this Dectorus detector, is already giving us all of this information in an HDF5, in a Nexus-like format. So I just took that, put it in here. You never know what you might need. So this goes into ridiculous depth. I can find out for each detector module what their flat fields are, how they've set the trim bits for every single pixel. You hope never to have to use this data, but we've already had 2 troubleshooting cases where data like this has been actually super useful. So you see that many of these metadata data sets, like pixel mask, they're actually multidimensional. In the case of our simple instrument, it's 2-dimensional. In the case of I-22, they go up to 5 dimensions sometimes. So you can actually see these data sets, so not just the end result, which is shown over here, but you can also go back and go like, okay, but what does that look like in 2 dimensions? Let me try and improve the color map. Okay, that doesn't work. You actually have much more information in here, which is also multidimensional, which might help you. You can put microscope, inline microscope images in here as well, so you have an image of the sample. You name it, you can put it in this HDF5 structure. Super handy. It's sort of like the MongoDB variant that you can just dump whatever you have in there, and later on you can figure out whether you actually need it. Oops, I actually forgot one thing. Now, alongside this, this data is also the process data. So when we record data, we also correct it. So we have all of the processed information in here as well, not just the result in Q and intensity and uncertainties and so on, but also the entire processing tree as a sequence of steps with all the necessary metadata to reproduce that, and some intermediate data sets, because in this whole data correction pipeline, you might have some points where you want to look at some of the intermediate data or some alternate data views. So you can store that in there as well. It's actually super useful. Yeah, you can actually rebuild your entire processing pipeline from the information in here, and this program does that automatically. So back to the topic at hand. So yeah, there's a lot of extra things that we need on top of this. So when you start developing these things, you have to feed in a lot of extra information. Thanks to Zoom for putting that bar back in place. There we go. Right. You actually need a lot more extra information in there. You need experience with HDF5 and Nexus, maybe EPICS, which is a control system. Lots of Python knowledge goes in there. Some idea about databases and so on. So I've started calling myself a full stack small angle scatterer now. But you see, there's something I haven't talked about, and that is related to this. Because we are reliant, or we were reliant, on users providing us with samples and sample series. And this is great if it's just a handful of samples, but now that we're able to process so many samples, we're actually finding that the users are not providing us with enough. And whenever they come to us and say, oh, I want to give you a couple of samples where I changed one parameter, and then we say, great, please bring us like 10 or 15 samples. And they kind of look difficult at you, and they come back to you and they come with 4 samples, which were synthesized on different days, with different lab temperatures and so on. One of them is an outlier, And then you have 3 data points left, and then they say, so what can you tell me about the trends in my samples? And I say, I can't tell you anything because I only have 3 data points. So we needed to provide them with a way that they could provide more, that they could give us more consistent, well-documented sample series. And of course, we turned to robots for that. What we did was to build up our own synthesis robot from more or less common laboratory equipment. Here's an idea about the equipment that we have. Some of this is good, some of this is less good. You can ask me which one I would recommend, and I'm very happy to answer that. On the hardware level, we connected these things by means of either serial connections, not USB, because USB is a pile of crap, but normal serial connections, or Ethernet connections, because many devices now also have Ethernet ports and a communication protocol. On the virtual level, we connected things through EPICs, or most of our laboratory hardware is connected through EPICs. Some of them come with their own libraries and so on. That's perfectly fine. EPICs runs alongside. Now, this is an industrial control system which is commonly used at synchrotrons and neutron sources. Very large facilities with lots of stuff that needs to be controlled. Definitely overkill for our little robot, but it's easy to install, has long-term support, etc. And that provides you with a virtual communication bus to which you can plug in your various loggers and controllers, and you can connect all of your hardware. It's actually working really, really nicely, and it's simple to set up. The robot itself looks like this. Well, this is a rendering. Makes it a little bit easier to see. We have some stock solutions on the left-hand side and one more small one on, on the right-hand side, and one small one on the left-hand side. We have in the middle a robot arm. We have lots and lots of Falcon tubes where we do our reactions. In real life, it looks like this. Of course, the robot arm moves. It can bring these outlets to either one or more Falcon tubes at the same time. So you can inject your reactants into one or into 2 Falcon tubes. You'll notice that for our robot, we decided against using these multiplexing valves. So all of the lines are kept separate. The reason for this is that these multiplexing valves, which may have multiple inlets and one outlet, if you use them, you need to think about cross-contamination, how to avoid that. You need to add rinsing steps, which is unnecessary and not all too good for the environment. And you have dead volume to account for. But if you keep your lines separate, those problems disappear. Highly recommended. Those valves are cheap and reliable, and they can be controlled with an Arduino. Actually, one of the newer industrial Arduinos will do just fine. So the first thing we did was to look at a very, very simple reaction, the ZIF-8 synthesis. This is the synthesis of a metal organic framework. This is sort of a cage-like structure that you can build up with a metal center and an organic linker. The reaction goes like this. You add a bit of solvents to these components, in our case methanol. You add these two together. You wait 20 minutes and you've got your metal organic framework. It is really that simple. So why are we even bothering with this? Well, it turns out that if you do these reactions and you do a round-robin study, that the reactions like these are not very reproducible either. Even super simple reactions like this. Now, there's a little bit of a discord that we can't replicate something like this, and on the other hand, we're having super advanced materials being developed. Recently there was talk about superconductors, also not very easy to reproduce. And I think the problem with this whole reproducibility here is that we have issues in science, in particular in the way we write down our experimental procedures in papers. Here's one that I lifted from a metal organic framework paper. It says you add these solutions under agitation at room temperature. I don't know how hot your rooms are, but our laboratory spans temperatures from 20 to 28 degrees. Stirring, not further specified, continued for 20 minutes, and then centrifuged, and it was washed, and no details whatsoever. The problem with this is that there's not enough information to really reproduce a reaction. Also not for machine learning. And I mentioned that specifically because there are groups that are working on ingesting experimental procedures from published papers into their machine learning system, and then asking this system to come up with synthesis procedures for yet unknown materials. But those synthesis procedures will also not have the necessary detail to really create a reproducible reaction, because it wasn't there in the source information in the first place. So work needs to be done on creating information that does have this. Here's a schematic overview of the robot. What it actually does for this reaction is that we set some of the parameters. We then aspirate with our syringe injectors a little bit of the reaction solutions, switch the valves, bring the robot head over to the Falcon tubes, inject one liquid into one Falcon tube. So you need to keep track of which Falcon tube is doing what, but that's not really a big problem. We then rotate the outlets, and then we inject the opposite liquid into the Falcon tube. You wait 20 minutes, and then the humans get to work, because we don't have a robotic centrifuge, we don't have a robotic oven. So there are still some manual steps to be done here, but we record them as well as we can. We can synthesize more than 100 samples a day. It's about 120 if you really take some effort, put some effort into it. So it's no problem in this case that there are some bottlenecks, because if you do 120 samples a day, it takes me months to measure that kind of samples. I now have a library of 1,200 samples. Every sample comes with detailed logs, and when they come out of the robot, they look like this. It's absolutely horrific. I don't expect you to read any of this. What we then do, what we actually spent an inordinate amount of time on, was to convert that into a nexus structure. I will show you what that looks like. So we have a directory structure to organize our experiments. We have 20. Our experiment series, and in each of these we have space for analyses and measurements and syntheses as well. And each of these syntheses for each of the samples is then converted into a tree-like structure. So that, yeah, the right-clicking is my nemesis. There we go. Here we have one of these syntheses. So what we have in here is metadata on the equipment. This is equipment set number 3. This consists of these components. Each component has a detailed description. It has a price. How much does it cost? How much did our robot arm cost, etc. And we specify things down to the, I need to look for this, down to the stirring bar, right? To whichever stirring bar we were using. We have chemicals. We have things like starting compounds defined, where we got them from. Then we have, stock solutions in mixtures with a component list, component masses, each one also with units. I have to keep bringing that up because units are super handy once you get them working. And even the synthesis procedure for that stock solution is detailed in here as a sequence of steps. Let me fold that up again. We have the reaction mixture. The reaction mixture also has the vessel specified that the reaction was done in. And then we get to the actual synthesis. This consists of a synthesis log of every single step that happens in the synthesis, like when the robot arm moved away. It also links to the device that actually did that action. So we added that relatively recently. Let's see if I can find another one. Humidity, yeah, there's a quantity there with unit and so Now this you can then use to get some derived information, some metadata, which might be of use for you later on. Things like what is the age of your stock solutions when you did the experiment? Because some stock solutions go bad. What was the reaction time? What was the synthesis yield? Where do you get this information from? Or from which message did you get this information? And so on. Things like laboratory notes are normally also in here, but this one doesn't have a laboratory note. So that's the way we've sort of structured our synthesis information. All right. We then do small angle scattering experiments to get the information on the phase identification and crystallite size, but also on the particle size, morphology, and size distribution. So here are 400 of these measurements. If we zoom in a little bit on the different sections, you see, well, there's some X-ray diffraction information here, which is not super exciting because you're either forming ZIF8 or ZIF-L or a mixture of these two. That's the only two things that you can form. But for the small angle scattering section, you see there's a big difference in particle sizes that you get. And this is really the thing that we were focused on. Of course, we checked whether we could consistently repeat reactions, so we did the same reaction over the course of several weeks. That works just fine. These patterns are exactly the same, and if you don't believe me, I understand, which is why we got size distributions as well, and we find out, okay, well, we can actually assess the mean radius of these particles at 71 nanometers, plus or minus a few percent. So good reproducibility. And then we started trying to discover things. So we tried to find out whether it matters whether you pour one solution into the other or the other solution into the one. And for good measure, also at the same time. We varied other things as well, such as injection speeds, concentrations, residence time, stirring bars, washing steps, and so on. And there's a huge difference. It turns out, if you, depending on the injection order, you actually get a difference in particle size of up to a factor of 4. Injection order and speed really matter. Now this is just particle size, which I'm showing here, but this has a huge impact if you're doing things like heterogeneous catalysis with your particles later on. Because the outside accessibility of these particles will be hugely affected by how large they are, right? Smaller particles, you have better accessibility. So if you want to compare, you really need to make sure that you have the same size of particles. Of course, we have not just average sizes, we have all size distributions, but just to make things easier, I'm just showing the size. We found out that stirring speed matters, as you would expect, but also that the stirrer bar shape matters. If I have a 15 millimeter rectangular rod, it gives me 50% difference in particle size than when I have a 15 millimeter ellipsoidal stirring rod. So don't just grab any stirring rod from your drawer. It has to be a specific stirring rod to get a reproducible particle size out. This we were a little bit surprised at. Yeah, of course, the size distributions are different, but you know, things like these matter. And I'm from a chemical engineering background. You know, we get told this all the time, but it is super hard to really reproduce something. So you know, you really want to be sure that you organize all of these. Now, I just wanted to show you before my conclusions the Synthesis Explorer dashboard, because we actually developed something like this. There we go again. We actually developed something just to help us visualize these data sets. So here on the left-hand side, I have, well, not all of my syntheses, but I have a large fraction of my syntheses. I have 740 syntheses here. Each dot represents a synthesis, so I can hover over it and see some of the details of that particular synthesis. And now you can plot different things against each other, like reaction time versus chemical yield, and you can see whether that matters. Well, it matters, but we have lots of different experiments with lots of different concentrations in here, so it's kind of hard to see for this. But we can also link them for the samples where we actually, which we've actually measured so far, link this information to the mean diameter, and we can find out, you know, for a given reaction, what was the scattering pattern, what was the size distribution for this. And in principle, you can now add a big button underneath saying, reproduce this reaction, give me more of these particles with this size distribution, because that would actually work. Now, not all fits are great. And we do certainly reach the limits of our machine for some of these samples, but this one's not too bad. So yeah, the current bottleneck is really the ability to measure these 1,200 samples. We've measured, I think, 400 so far. I've only represented like 100 in here. Yeah, that's the bottleneck again. So we're back to X-ray scattering as the bottleneck, not the sample preparation. So one final word about whether any of this is going to be available. Yes, actually all of it is going to be available. We're sort of fine-tuning these HDF5 structures at the moment. But you will get libraries with syntheses. We also have a physical library of samples. This, of course, does not let itself be distributed so easily. But for each of these samples, you might be doing a measurement. So these measurements will become available as separate libraries. We will get analyses libraries associated with a measurement or with a measurement series. And these might eventually end up in interpretations. Now, you can already see where this is going, because you might do multiple types of measurements, like small angle scattering and electron microscopy. You might do a different analysis on that then feeds into your interpretation as well. Or you might do alternative analyses. There might be more than one way to slice that pie. So all of these things should become available as they are being produced. And like that, you will be able to feed in information from multiple syntheses and hopefully get some correlation between these parameters. Yeah, I actually skipped over one particular visualization, but that doesn't matter. It was lab temperature versus chemical yield, and fortunately there's no difference. Anyway, just to conclude, I've shown you a couple of things. I've shown you what you can do with by looking at your experiment from a holistic point of view and trying to optimize that whole thing. You can get great efficiency improvements, great improvements in the metadata you collect. And you can then start using laboratory automation to feed into this whole measurement process. And hopefully, this way we can get a full grasp of the entire experimental procedure. But these things take time. They can take a lot of time. They take a lot of stuff. Now, at BUM, we have an enormous amount of stuff, but they also take a lot of people. And this is where we're not doing so well. We really could use a lot more people to really exploit this this platform, this concept of doing things in a holistic fashion. So, yeah, if you're curious about any of the things that I talked about, please do contact me. Always happy to receive emails. I try to answer all of them. I have an email address. You mentioned already my weblog earlier on, lookingatnothing.com. I have a YouTube channel with several videos on there. And I'd like to end by thanking my colleagues Glenn Smales, Aaron Chambers, Ingo Bressler, and Julius Frontek, and all of the other positive influences in my personal and academic life. Thank you very much for your attention.